Okay, so can you see the screen I'm sharing?
Yeah,
Yes.
All right. Okay, so you have already seen for exponential growth, we have some exponentials to solve, spatially when we are asked to calculate the time duration, that means n. So if we are asked to solve that, you can clearly see that n is an exponent. That's the power of a certain expression. So we need to see how can we solve that. And for that, if you have the book open in front of you, that would be nice. That's page 184, as you can see. Okay. And for solving exponentials, we actually need uh, logarithmic properties. Why is that? You will soon see uh, at the very end of page 184, you can see a box. So I'll start writing now. So let's start sharing my screen of my iPad. And here we go. Okay. All right. So if you can see the box, you can see the relation between exponential and logarithms, which is if we have um, a common logarithm, which we say of base 10. Oops, sorry, let me use different color. So of base 10, we say the common logarithm is written as this, log of x, where this log means logarithm. It's an operator. Now, a quick reminder, what is an operator? An operator is kind of a machine. Oops, sorry. Where you give something as input, that operator does some different tricks and gives you something different as an output, like a machine. When you uh, give ground coffee in the coffee machine and water in the other um, place where you actually um, provide the water, it after a while it gives you coffee. So that's the coffee machine. So the operator is actually like a machine. It gives you something completely, not maybe completely out of the world, but um, as a chemical property, it gives you something different. For example, a coffee, right? So this logarithm is an operator. Whatever you plug in for x, if you operate logarithm on that, it will give you a different result. For example, the logarithm of 1 is 0. Okay, so it actually is working on 1, and then in return, it's giving you a 0. So that's why I say it's an operator. Anyway, so that's the common operator. Now, what is the relation with this with an exponential? Because we said for solving exponentials, we want to know the properties of logarithms. So here is the relation. For the normal logarithm or common logarithm, we say it's log of x, and the common exponential of base 10, we say it's 10 to the x. Okay, so that's how we can solve. We will soon see one or two examples, and hopefully it will make sense. Okay, so we have certain properties of this. So the first property will be, let's say, logarithm of x to the n. So that's exponential working on this x. Okay, that's an x n, by the way. Looked like m. Okay, and the property is whenever we have a situation like this, you can straight away write this. That means you can take the exponent in front and write it like this. Okay, similarly, we have, not similarly though, we have an um, we have a property which is this. If we have an equation like this where 10 to the a equals to b, so we can actually rewrite it as logarithm of b equals to a. Now here is a quick or rather really interesting fact. Why can we write that? Okay, so let's just show why can we write that, and then uh, I'll show how can this be used in our problem. Okay, so property is whenever you have anything like this, when you have an exponential, if you take logarithm in front of it, that means if logarithm works as an operator, you can straight away write x. Okay, now why is that? I have already shown that you can take the exponent in front, so this x could be taken here, log 10. And if you remember, I said it's a base 10, so base 10 of log 10 gives you 1. If you have the calculator, you can check yourself. So that's how we can actually reach this x. Okay, so that's why this is true. Similarly, same goes for this as well. 10 of log x can be written as x. So I want you guys to remember these properties. This will not be given in your exam. You just need to remember these four properties. If you remember, then you can easily um, solve, I guess, most of the problems, if not all. Okay, so just remember these four, and let me solve one problem, and then I'll give you time to ask questions. Okay, let me just solve one problem first. I think it will uh, kind of make things just a little bit more clear. Okay, so let's say we have, let's take example 9. Okay, let's see some worked out problems first. Example 9, let's start with b. We have logarithm of 1,000. Okay, you can say log of 1,000, and if you know that this 1000 can be written as 10 cubed. If you're wondering how, 10 cubed is basically multiplying 10 three times, right? So 10 times 10 times 10, which is technically, or rather, it's equivalent to 1000, equivalent to this 1000, right? So we can sorry, rewrite this 1000 as 10 cubed, right? Now, let's eyeball the properties we have and see which one we can use to kind of simplify it. So you can see we can use property 1, right? Because we can see an exponent here, right? Can you see that? So let me rewrite the property here so that we don't need to scroll to show that property every now and then. So this is n log x. Okay, so this is the property we're going to use. Just compare this and we can just uh, replicate what we have here. Okay, so on this occasion n is 10, or rather 3, my bad. N is 3, so this 3 will come in front and we'll have log of 10, right? And another property we know is log of 10 is 1, because this log has a base of 10, so it will give us 1. So 3 times 1 equals to 3. And you can actually check that on your calculator as well. If you plug in log, then 1000 equals, it will show 3 on your screen. Okay, you can see a log button in your calculator. Um, I think it should be in the second row. Yeah, in the second row, whichever calculator you have, it should be on the second row. You can see something uh, called log as a button. If you plug in that, then you can actually write 1000 next to it, and if you plug in equals then it will show 3. And that's the algorithm. That's how it works. We can solve it on hands as well, because it's a smallish problem. Even if it's larger, the calculator will actually rather use the same algorithm to solve it. Okay, now let's see one more problem. Uh, okay, let's see, log of 1 over 100. So for this one, you can use the property that exponents can be written this way. So if we have x to the negative n, you can write it this way, 1 over x to the n, right? If you haven't seen this before, you can remember this. If you already know, that's perfect. So if you have a negative exponent, you can take the reciprocal of it with the positive, or rather the alternate exponent. Okay, so 1 over x to the n is basically x to the negative n. So we can use this property here, and excuse me, and before that I'll write 1 over 100 as 1 over 10 squared. The same reason as this, 100 can be, or rather in the opposite direction, 100 can be written as 10 squared, since 10 squared is multiplying 10 twice, which gives us 100. And now if we use this property, we'll get log of 10 to the negative 2, right? And then we'll use this property where the exponent comes in front. So now this will be negative 2 log of 10, and log of 10 gives us 1, so it's negative 2. Again, you can check that, you can cross check this using your calculator. Okay, let's take a break now and see if you have any question. These are really basic steps. Your problems will require you to solve more sophisticated one, that's for sure. So if you have any doubts, you can clarify those now. Anyone, any question? You can unmute yourself.
I have a question.
Yeah, sure.
So log of 10 always equals 1.
Well, yeah, the common log of 10 will always give you 1. That means whenever the base of it is 10. So the common log has a base of 10, but ironically, we have different bases as well. We have log of base e, which is written as ln. You will see some of these in the higher classes as well. We have log of base 2. We can actually have any number um, as the base of the log, but the most common one is the base 10. It's actually written as this, where the base is just below the log. It's written like this, the standard format of this. So it's the most common one. So we avoid writing the base when it's 10 and write it like log. And whenever the base is 10, that means whenever we write it like this, yeah, it will always give you 1.
Okay, thank you.
Mhm. You can remember this as well. Um, yeah, I think I should write it as well. Yeah, you can have this as a property as well. Yeah. Okay. Any other questions? Okay, then let's move on and see what can we do to um, solve exponentials. One more thing. Um, what if the value we have is different than the exponent of 10? Let's say you have log of 15. You cannot really express it as the exponent of 10, like the way we have done here, right? Like the way we have done for this and this as well. What if we can't really express it? So for your problems, you can easily use your calculator, okay? Whenever you don't have this, even if you have exponents of 10, you can definitely use your calculator. But if you are asked to show how can you solve it, then uh, I will give you a problem where you can um, express those as the exponent of 10. Okay, I'll not give you a problem where you can't really express it as the exponent of 10, and I'll not say that, hey, show your work, how can you solve it? If it's not expressible as the exponent of 10, I'll not ask you to show your work. You can just use your calculator to plug in whatever value it gives you. Okay, all right. um, so let's see a question which might be a part of your next homework or even in the exam later this month. So let's see example 11, and let's try to solve Let's try the most complicated one. Okay, so okay, I think B and C is pretty similar. So let's try C. Okay, so it says solve 2 times 10 to the x equals 8. Okay, so the reason I'm repeating myself, the reason we're trying to learn how to solve this, because often we'll be asked to find the time duration n, and for the exponential growth, if you remember, it actually looks like this, right? It works as the exponent. So we'll be asked to solve, if we are asked to solve solve for n, we actually need these properties, or we need to know how to solve this. Okay, so let's start. So 10 to the x equals 8. So you can divide both sides by 2, right, to get rid of this. So 10 to the x will give us 8 over 2, which is 4. So we have 10 to the x equals 4. Okay, now what should we do? So we know one very good property, which is this, right? The exponent comes in front, but we don't have log here, do we? We don't, right? So we can take log on both sides, because if you remember, whatever we do, um, we need to do that on both sides. So let's take log on both sides. And now we can use this property. So x will come in front. Log of 10 equals to log of 4. Log of 10 will give us 1. So x equals log of 4. And this is actually what we are trying to solve. You can see the only unknown value here is x. So we're trying to solve it for x, definitely. And we are almost there, because you can see on our left, we have x. We have somehow isolated x, right? When we are trying to solve an equation for an unknown value, we always try to isolate that, and we have successfully done that. I shouldn't use the notation here. Okay. Now, as you can see, we have a value which is not an exponent of 10. We can't really express it as uh, the exponent of 10. So now you can use your calculator. So if you use your calculator, let me see what it shows. Log of 4, it gives you 0.6020205 rather, 9. Okay, we can instead write, because we have a bunch of 9s after this, so you can write 0260, yeah, up to 5 decimal points. Okay, so this is the solution of the given problem. So if you are asked to show your work for these problems, you need to write it up to this. Then you can use your calculator to show this value. Excuse me. Okay. Okay. Now, yeah. Any question before we move any further? Because you can see things are getting more and more sophisticated. So if you have any doubts, my humble request to you guys to clarify those. Uh, and now is the best time to clarify problems, if you have any, of course. Anyone? Any doubts?
Can we go through another one similar?
Yeah, sure. Okay, let's try one more. let's try, let's take one from the exercise. Okay. Where is the exercise? Okay, I think we can generate one and try ourselves. Yeah, let's generate because I'm not seeing the exercise anywhere near the page we are now at, so I think it's quite quite a big topic here. Anyway, so let's try this. We have, let's say, 10 to the x times 6, let's say, equals to 9. Okay, and first of all, we are trying to solve it for x, because you can see that's the only unknown value, or rather variable here. So we'll try to isolate that first. So we can divide both sides by 6. If we do that, we'll have 3 halves. Then, as we're trying to isolate this x, we'll take log on both sides. And now we can use the property that whenever you have this format, the exponent comes in front. So we'll have x equals to log of 3 halves. We have finally isolated this. And if you have the calculator, you can plug in log of 3 halves, or you can write log of 1.5, whichever looks good to you. This is technically the same thing, which will give you 0.1761 up to 4 decimal points. Okay, so this is your answer.
Thank you very much.
Mhm. Okay, so if you go to page 186, they have this summary. I mean, whatever I have discussed so far, they actually combined. They have actually combined all of these and made a summary for this. So they have said isolate the exponential. That means on one side of the equation, uh, you need to have the unknown value, whatever it is. It could be x, it could be n, depending on the problem. Try to isolate that. Okay. Um, so for that, you need to take log on both sides, right? And use the exponent property, which is, what is that? Which is this one, the exponential property, right? And then you just need to uh, see what value it gives. Okay, so let's quickly start example 13, because I don't want to go over time anymore. So let's try example 13, and then we'll take a break for a minute or two to see if you have any question. Okay, so example 13 says if Olympia is going according to the equation Pn equals 245 1.03 to the n, where n is years after, so n is years, and the value is actually um, from 2008, and the population is measured in thousands. So this is basically this, okay? It's actually in thousands. Find when the population will be 400,000. So that means we're looking for the n where the population will be 400, okay? Right? We're looking for the n. Now you can see we'll have to solve the exponential, right? And we'll use the property we've seen so far. Now it will make more sense, hopefully. Okay, so it will be 400 equals to 245 times 1.03 to the n, right? Because both are equal to both are equal to Pn, so you can write this equal as well, right? Now we have already seen problems like this, right? Isn't it exactly the mirror image of a problem like this what we had the last time? 6 to the 10, 6 times 10 to the x equals 9. Can you see the similarities? Can you see it's actually the resemblance of the same problem? So n is x, 245 looks like this. This is our base. Okay, let me use a different color so that it makes more sense. So you can see the color I'm using to show the similarities, right? Can you see that? It's exactly the same problem with different numbers, that's it, right? So let's solve it. Let's try to solve it. So once again, let's write this on our left first. You don't need to do that though, but often it looks good and psychologically it helps you. Okay. Now what should we do next? Don't look at the solution. Try to use the idea from the previous problem we have seen here. What should we do next? Anyone?
Would you divide by 245?
Very good. We're trying to isolate this. So we'll first divide both sides by 245. So let's do that. You can use your calculator to see what's the value of this. 245 will give you 1.6327 up to 4 decimals. Okay. All right. And now we have 1.03 to the n equals 1.6327. Now what should we do? What's next? Anyone?
Log both sides.
Very good. So let's take log on both sides. You can see if you just remember the steps, it's really, really easy. Okay. So now this n will come in front, right? Using the exponential property. Excuse me. N times log of 1.03 equals log 1.6327. Now what should we do? Can we eyeball this and try to use our intuition to see what's going on? We're trying to solve it for n, if you remember. What should you do? It's not exactly log 10, right? So we can't really plug in 1 in place of it. If it was log 10, we would have plugged in 1 straight away, but it's not log 1, or rather log 10.
Can we divide both sides by log 1.03?
Very good, because if you remember, we are always trying to isolate the unknown variable, whatever we are asked to solve it for. So we're trying to solve it for n. So somehow or other, we need to isolate that. That's the most important thing. So as this is a product, if we multiply or rather divide both sides by, let me use a different color. If we divide both sides by this, then we can see, we can actually imagine that this n will be isolated, right? So we can do that 1.6327 over 1.03. And now definitely you can use your calculator to get the final result. So log 1.6327 will give us 0.2130 up to 4 decimals, okay? And log of 1.03 gives us 0.0128 up to 4 decimals. Now we can divide this as well. So 0.2130 divided by 0.0128. Okay, so it will give us 16.6406 up to 4 decimals. Okay, let's see what we have in our book. Okay, so they have 16.591. No problems with that because they have taken, I can see, up to 3 decimals. So that's why they have slightly different value. No worries. That's technically the same thing because we have taken more values after the decimal point. We have taken up to 4 decimals. They have taken up to 3 decimals rather. So that's why they have a different result, but that's still uh, uh, more than enough for us. Okay, so that's it. So that's the value of n. You can see they have used this sign. That means it's not exactly 16.591, but it's approximately that, because you can see we can actually, if you have used the calculator to actually get the value, you can see you have more values here, to be honest. I actually rounded up to 4 decimals. So it had a continuous, uh, or in maths we say infinite number of decimal points. Uh, so we can round it up to a certain value, up to 3 decimals or 4 decimals. So it's not exactly that value, but quite close to that. So we use this notation for that. Okay. Okay. Any question now? I wish I could show you the entire um, problem altogether. Let me try. Okay, yeah, this works. I think you can see the entire problem now, right? Now eyeball it and see if you have any question. Anything, even if it looks kind of stupid, I'm more than happy to answer it. Okay, don't hesitate at all. You will be asked to solve this type of equations, this type of exponentials um, in your next homework and obviously in the exam as well. So it will be really, really crucial. And whenever you will be asked, most often you'll be asked to show your work as well. Okay. So you need to know what the steps are or how did you reach that conclusion. No questions at all? Perfect. Let's move on then. If I'm going too fast, you can definitely slow me down by asking questions or saying um, go slower. I'll try to do that. I'll try to pace up with that. Okay. Now let's see the next problem we have. Excuse me. Okay. Okay, so for that, on Wednesday, your pre-class assignment will be try it now 4. Okay, and for that, we'll try to solve a similar problem, which is example 14 now, so that it makes sense. Okay, you can hopefully use this idea to solve try it now 4. And hopefully I'll post a new homework today. So keep an eye on the announcement as well.
What page is Try It Now 4 on?
It's 188.
Thank you.
Okay. Now, the problem says polluted water is passed through a series of filters. Each filter removes 90% of the remaining impurities from the water. If you have 10 million particles of pollutant per gallon, how many filters would the water need to be passed through to reduce the pollutant to 5 particles per gallon? Okay, so this is a long question, but we only need the information it has rather. We don't really need the extra English phrases, to be honest. So let's see. All right, so we need, I guess, how many filters? So I guess, yeah, we're looking for n here as well, where n is the number of filters we'll need, and pn is given, which is 500, obviously million of gallons, I believe. And what is p naught? Let's see, p naught, 10 million. Yeah, it's given. So you can see we just need to look for the information we have. So you can see p naught, the initial particles, however you pronounce it, is 10 million. Okay, and what else? Oh, so if you remember, this is the exponential growth, right? So that means if we're looking for n, we need pn, p naught, and r. We have only 4 things to look for, and out of these 4, 3 will be given. The other we will try to calculate. We're looking for n, so we already have p naught. That's already done and dusted. We have pn as well, because it says we are looking for how long, or rather how many filters will it take to uh, reduce it to 500 particles. So that's our pn. So pn is done as well. Now the next thing we need, the last thing we need to solve it for n is r. Can you eyeball r here? If you can do that, rest is pretty much what we have done in the previous problem. If you just can eyeball and find r, that would be
0.9 would be 90%.
okay, 0.9. And here the most important thing, or most tricky, I would say, would be, yeah, definitely it looks like r equals to 90%, which is 0.9. But the funny thing is, you can see it is removing the impurities from the water, and clearly the value is getting reduced. If you remember, the last time we talked about this, that uh, this R could be positive, could be negative. That means if it grows exponentially, then it's positive. If it's decays, if it's getting reduced exponentially, that means if it's going this way, if it's increasing, then R will be positive. And if it's going this way, that means if it's decaying, then R will be negative. Now, we can actually eyeball it. You can see from 10 million. Oh, God, that's so irritating. Okay, so you can see from 10 million, it's getting reduced to only 500. Can you see that? So that's why this R should be negative. That's really, really tricky here. If it's growing exponentially, R will be positive. If it's decaying exponentially, R will be negative. We can see it's getting reduced. So this R will be negative. Okay, now we have our problem. We have the setup. So 500 equals 10 million means 1, 2, 3, 4, 5, 6. Is it right? No, I think I should have one more zero. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. And so the formula is P naught times 1 plus R to the N. So 1 plus R is negative 0.9 to the N. So it's 1, 2, 3, 4, 5, 6, 7. 1 minus 0.9 to the N, which is 1, 2, 3, 4, 5, 6, 7. 0.1 or 0.10. It's actually the same thing to the end. Now, if we solve it like the way we have solved the previous couple of problems, we'll get our n. Is there anyone who thinks that he or she might not be able to crack this? You can just let me know. But this is exactly this can be done exactly the same way we have done in the previous 2 or 3 problems. The most tricky part could be to reach this final formulation. If you can formulate that, you can see this is exactly exactly similar to the problems we have solved so far. Okay, any question from today's discussion? Anyone? If you
How do
want
we
to, yeah, sure.
input? I keep getting a domain error when I'm trying to do a negative log.
Sorry.
When I try to do the net log of negative 0.9, I keep getting a domain error.
Oh, okay. So that's a good point, though. I'll run short of time, so I'll keep it short. So log always have a value which is non-negative. You can't plug in a negative value and get any value because this operator only works for non-negative values. That's a good question, though. Yeah.
Very good. Thank you.
Okay, so let's stop it here. And on Wednesday, you have try it now 4 on page 181, 188, I believe. Yeah, 188 before we meet. And you will have your next homework posted today. I really believe I'll post it today. Just look for the announcement. And yeah, I'll meet you on Wednesday.